everyone. Welcome to Financial Time Series Modeling and Forecasting class. I'm your instructor, Myung Kim, of this department. This format is very new. This course is usually offered in Korean. Starting from last year, it is offered only in English. And starting from this year, this is part of our open courseware system, which means everyone else who wants to attend this class, they can access this one remote. So it's a very different scheme. At the same time, this is the way university is being changed these days. So if this lecture is really good, I expect more than 30,000 students attending this course, and I have no time to sleep because I have to grade things, right? So I think it's a very exciting experiment. And of course, because this is the start of this new system, there may be some confusion or inconvenience. At the same time, some anxiety from student side. Hopefully you can bear with me, and hopefully we can enjoy this course. Okay, what I like to do today, first I want to talk about class rules and brief introduction about the course and some of the requirements and some of the administrative things like class rules. And half of the lecture will cover introductory part of the course, so you can have some sense about what kind of course this is. This one, 3 credit a course, and of course hours written here Monday and Thursday here, and office hours basically right after class, Monday 4 to 5 p.m. My room is 7-Eleven, so 7th floor this building. 7-Eleven means I should open my office all the time, but I'm not that good keeping time. So if you can't make this time, then you can make an appointment, and you can see my address. Okay. Frankly, this course is a little challenging one. Although there are many demands from the field as well as academic community about time series techniques, but still it has a little bit of mathematics, a little bit of linear algebra, a little bit of statistics, but more importantly, it requires many of your patience. So as you can see here, we learn a model. Basically, it's about forecasting things. We try to learn the data and try to persuade data sort of to confess their story about what's going on behind the system that generate that kind of data. So many standard models like ARIMA model, we will learn that shortly. Volatility models, we live in very volatile, uncertain period, like quantitative ease is expected to be lifted up starting from October. Many experts forecast that. What would be the effect of lifting up of quantitative ease on many interesting time series like interest rate, GDP, CPI, and so on and so forth. So we try to understand how the data is generated and using, and then build the model, and then eventually we'd like to predict the future behavior or path of time series of our interest. And there are many models other than standard ARIMA model or volatility model, thing called state space model. This is a very powerful tool that describes some relation between observed variable and sometimes something that is not observed, like expected inflation. Expectation is made by people. It's not a data, right? But in somehow you need to model that explicitly to build a forecast model. So we'll learn some model like state space model to handle that kind of problem. And sometimes we work with several time series, not single series. So we need to consider vector model. And also sometimes you need to generate forecast in the long run as well as short run. And depending upon your purpose, you can use different type of model to generate the forecast. So there are many things going on, and one semester is sort of short to cover every detail of that. But I try to make this course, design this course so that you can learn as much content as possible as an undergraduate major. Okay? Also, this course is strongly recommended to students who's interested in registering next sequence. This is an internship course. Last year we had 34 students doing their internship in various places like a consulting company, banks, security companies, and asset management company, and so on and so forth. But when I try to arrange that kind of internship, they ask us to educate you to a certain level, particularly your ability to analyze data. So this is strongly recommended. If you can read Korean, this is the title of that course in Korean. And I don't know whether we all should sign up for this one to make this course as an open courseware, but I was not asked, so probably you won't be asked either. But this one is going to be available to many students who cannot come to this course. But that doesn't mean that you don't have to come to show up here every time. You have to show up every time because I can't keep the record attendance. Okay, so that's that. All of our activities have a goal. Right? I listed 3 to promote concrete understanding of various time series methods. You need a basic tool. So I try to make you exposed to those various time series tools. And then, well, even if you have the right tool, for instance, even if you have drivers and drills and those tools, but you can't fix your car by yourself, right? Unless you learn how to apply those tools or methods to a particular problem. So I try to show those examples so that you can learn you can achieve second goal. And then sometimes to analyze or build time series model, we can use canned software like eViews, SAS, or there are many time series computer program. But at the same time, you may have to write your own code if those are not available as a part of the whole package, right? So we try to learn a little bit of programming this time. Okay, then the credit policy midterm exam will count 30% of your final grades during midterm week, and final week we'll have final exam that accounts for 40%, and assignment maybe 2 or 3 assignments, and class participation 20%, and attendance 10%. So they'll make up to 100%. Some typical rules. Last year it was embarrassing to receive 3 answers written in Korean, even though this is designated as English only class. So answer sheet is expected to be prepared in English. Hopefully no makeup exam. This is usually emphasized by instructors. No late turn-in, because the competition has to be fair to everybody. So you are given time, deadline for homework assignment, and you should turn in by that deadline. So keep this in mind. After due date, you can turn it in, of course, but won't be getting any credit for that. So we'll talk a lot about something that is random in this course. Random means something uncertain. Okay, so that a statistic enters in this area. Because we deal with randomness most of the time, so I try to apply the checking that concept for the checking purpose. Okay, textbook. The one below, I borrowed it from internet. Actually, this is the one I wrote with one of the professors at the other university. This one is very thick, written in Korean, and not required. So just in case you want to know some more about time series analysis that's not covered by Ender's book, which is our main textbook. This is one way, one textbook you can refer to. But you can focus on this one as a main text. I have not met Walter Anders. Actually, he is a chairman of the Department of Economics, Finance, and Legal Studies of University of Alabama, which is my former workplace. But when I left that university, he became an interim chairman, and then later a chairman. So we didn't overlap, so I don't know him. But his book is very intuitive, and of course very, very thin. So you can read it in a semester. Writing is very, very kind, and examples are good, and it covers, most of the subjects necessary for undergraduate teaching. So get your copy if possible, but it's fairly expensive. You need probably to pay $100 or more for that. So if you can't really afford to get your copy, I don't know him in person, but if you can't buy it because of your financial constraint, economists we talk about all the time, financial constraint, then you can try to keep up with our lecture note. It'll mostly cover what is written there, and of course the things written in other good leading textbooks. So don't worry too much about that. Okay, let me pause here for a moment and see if you have any question about class rules and other administrative things. So far, so good? Okay. Before I talk about tentative schedule, many of you may be a little anxious about, well, how's the midterm or final exam look like, right? Because in the end, you need credit, right? So here is my plan. Exam looked like this, and this is the answer I expected. So believe it or not, if you survive the course, you can answer those quite easily. Okay, so you can learn the format of questions and how to prepare your answers. So things like this one for midterm and final, I try to distribute this one. So don't worry too much about it. This is my portal, all written in Korean. I'm not sure whether it has English version. I think there should be. This is something called online lecture. If you have any, if you need any assistance getting things or getting an access to those material, you've seen my teaching assistant, Ms. Kim, Yeon Kim. You can ask her help, or you can ask her help to me. But when I press this one, that leads you to this screen. And actually, this is the course, Econ 261. This is very funny lecture code. Maybe they changed the lecture code. But this is the course. And I will check into this course where I can upload lecture material. Okay, lecture material. So I uploaded the course syllabus, the one you've seen this afternoon, and also lecture 1, introductory lecture note. Okay, and I'll keep upload those materials, okay, as well as some of the sample programs and the data. Okay, sometimes some leading material. So this is where you can get your lecture material. Okay. It's all tentative, but I thought that when I covered this material last year, I think the scheme went well, so I try to stick to that scheme as closely as possible. Week 1 introduction, we'll see a little bit about the software called eViews and Gauss programming, just introductory. The eViews program look more like this one, and it has many menus, and many of the time series techniques are already built in. So you can upload data, and then you keep press button and get some result, and result is stored somewhere. Like this one is called walk file, where, for instance, this exercise, where suppose you invested on something, so you have a portfolio. You purchase stocks, bonds, or some derivatives. Okay. You want to measure the change in value of your portfolio. Okay. So suppose that your value didn't change in the first date, so 0. Next day, you may gain, right? Stock price rises or interest rate falls. If interest rate falls, then the price of bond increase. So if you are holding bonds, when interest rate falls, then your value increases actually, right? So sometimes your value increases, sometimes your value decreases. Right? Can you control the rise and falls of the value of your portfolio? Can you control that? No, right? Stock price is determined someplace else. Stock exchange, right? Bond price, very similar, right? So we call it market risk factor. So typical market risk factors are stock prices, interest rate, exchange rate, commodity prices. And those are market risk factors. Because of that, your value of your portfolio changes, right? So suppose you calculate it using some time series technique and calculate it up to, let's say, 500 times. Okay? And then here, this one is something called histogram. So all those values, sometimes 0, sometimes positive, big negative. So big negative, big positive, some frequency. That's a histogram, right? And if you do this kind of exercise, you can determine, let's say, 0 means no change in the value of portfolio. And this is the case where you lose from holding your portfolio. Right? There's a concept called value at risk. It's the concept we talk about all the times in risk management. What is the maximum possible loss you can incur within, let's say, next 10 business days? So 0 means no loss. Positive means gain. This means loss. There's little chance, but still there is a possibility of big loss. Right? So value at risk measures this risk. So if, let's say, this interval is 1 day, so 500 days, and these are the possibilities in frequency. What is the maximum possible loss? They can happen within a 1 day period. Let's say maximum of, let's say, this much, with probability, let's say, 99%. So if you are running a security companies and run the portfolio on behalf of your customer, you have to be prepared that kind of big loss. Otherwise, you have to go for bankruptcy. So that kind of concept is typically introduced in terms of time series analysis framework, and these are the kind of subjects we'll be covering. But to facilitate that kind of analysis, we need to learn softwares. It could be EBIUS, SAS, or other softwares. Right? So EBIUS will look more like this one. A Gauss. When you start a Gauss, there's nothing, just blank screen. You have to write your own code, line by line. So it's very demanding task, right? But luckily, in many cases, all those programming consists of several parts, like setting up your problem, and then, if necessary, bring data into your program, and then do the analysis, and then report. the most difficult part is to write your program for the analysis. When those programs are not available, you have to write every line of the program. But these days, we have something called library. And this program, Gauss also has a library, like optimization library, that tries to find the minimum of some function and so on. So you can make use of those libraries so that you can make very compact program, but you can handle very complicated problem. Okay? Gauss was my favorite. It's still my favorite. But this summer, it was very hot and very difficult to find friends who wants to play golf with me because it's too hot and rainy. So I started looking for something new, something challenging. So I started learning new language called MATLAB. That does very similar job like this one. But anyway, you need to learn something, some programming language so that you can test your idea quick and also you can handle some problem that is not included in commercialized software. So this this particular program, we'll see that during the course. But when you actually implement that kind of program, this sample screen, Gauss screen, is something like this green line is what we call term structure of interest rate. So this is the maturity in years, and this is the interest rate. Okay. So the interest rate, 3-year interest rate, is something like this one. But if you actually look at real data, there's no bond which mature, let's say, in 2.17 years. There's no such a thing. There could be, but usually there is no such bonds available. So bonds are usually traded heavily, like at particular maturity, like 3 years, 5 years, 10 years, some particular maturity, right? Even if that is the case, still you need to know what is the interest rate relevant for 4-year bond. When actual transaction is made around 3-year bonds and 5-year bond, still you need to know what is interest rate for 4-year bond, right? So the way we proceed in that case is to define some curve and try to explain actual data. Okay? And this particular program we learn will find this dotted line as estimate for particular month. And if you have a data for the next month, then you can also find another fit, right? So if you have, let's say, 5-year monthly data, so 60-month observations, then particular model is fitted like that. That means you are building a model that explains our term structure behavior over time. And then you can use that model to actually predict future curve. Okay. So unfortunately, for those problems, those are not included as a procedure in eBuild or SAS or in other CAN software. So you have to write your own code. So in that sense, it could be a very powerful tool if you learn programming language. Okay, so these are softwares. And then regular lecture, we first start with something called stationary time series model. In the next lecture note, we'll talk about what is the meaning of stationarity and why that is important and so on. But these are the main contents covered in Ender's textbook, so we'll cover that one. But first, we start with autoregressive moving average model that is developed a long time ago, like during 70s in statistics. But the starting point is we deal with single time series first, okay? And then if you actually look at data, if this is straight line, you don't have to model this one to predict future. What you need is just a ruler, some stick, because it's extension, right? So this is a case of deterministic series. There's no variation. If stock price of Samsung Electronics moves like this one now, then should you buy this stock or not? Buy, right? It's going up and up and up and up. No uncertainty, right? But reality is like this. You can go this way, stay, or rise, right? So that's uncertainty. So this kind of variation, uncertainty, is usually measured in statistics by standard deviation, universal notation sigma. So this is a volatility, right? If volatility is big, then there is bigger chance of stock price going up, as well as bigger chance of falling stock, right? So more risky stock, right? Will that riskiness constant or varying? Many people believe that volatility changes over time. Okay. Interest rate also change, right? These days, the fear in the industry is that this might go that way. We don't know whether actually it will go up like that, but many people fear. Why? U.S. Treasury printed a lot of money, right? Quantitative easing. 1, 2, 3. So there are lots of dollars around the world, right? And big portion is flowed in to Korean market as well, right? Now they try to exit from that kind of policy. So when they stop this one or slow down this quantitative easing, that means the dollar, let's say, invested to emerging market like Korea, there has to be flowed out for the country, right? So, the typically when foreign investor want to exit from our bond market, typically what happens is stock price falls and interest rate rises. If interest rate rises, if you are actually managing bond portfolio as a manager, fund manager, if this rises, then the value of your portfolio, as I said earlier, that will fall, right? So the profitability is expected to fall as this one is expected. But the problem is, if you expect that is going to happen, then why not lower your bond position now? But the problem is everybody these days want to lower their bond position. Who's going to buy it? Foreign investors. Used to be that way, right? But no more foreign investors, and they will leave this country sooner or later. Many people guess that's going to be October. I'm not sure whether that actually happened or not, but that's one of the agenda I have to answer to those people in the industry later this month. But that's the uncertainty. So if you think of particular period as a more tranquil period, some more volatile period, and this number may not be the same, right? May not be constant, right? So if you expect that kind of bigger events, then you expect this one is going to increase, right? So we need to somehow model that one. So that's the modeling volatility part. Something we call ARCH or GARCH or multivariate framework, multivariate GARCH, and those models. Here is the interesting aspect of this particular model. Sometimes we econometricians know how to model things in principle, in theory. But when you actually try to implement particular models, you need to so-called something has to be estimated. Your model has to be estimated, validated first before you make a forecast, right? What if your model is perfectly okay, but you can't estimate those model parameters? That model has no practical usefulness, right? So this particular course, when everything fails, although this is the best model we can think of, but still life has to go on, and we need some reasonable alternatives, right? So we talk about those modeling issues when we talk about that part. Models with trend. Typically, this kind of, let's say, tendency to going, let's say, upward, we call it trend. Trend could be downward trend, or sometimes U-shaped. About more than 20 years ago, when I was a college, a graduate student, in a course, I was learned that commodity price tends to move U-shaped. So it's very difficult to explore those mines and those minerals. But as technology progress, is cheaper to extract ores, right, from ground. So it gets lower and lower, and then all the mines in an area is all those are depleted, and you have search for deeper or the ocean's bottom and so on and so forth, right? Very called Antarctic or Arctic area. So it starts rising. So if you look at, let's say, a 50-year period or 100-year period, there may be some kind of pattern like this one. We call it trend. Okay. A trend could be deterministic, like this straight line, U-shaped, or this trend could be stochastic, uncertain. There is a concept of trend, but it could be stochastic. And actually, almost all the time series, economic and financial time series, they are stochastic. They have this kind of stochastic trends. We'll learn more about what we mean by stochastic trend, but that makes time series modeling a little challenging, sometimes a little bit confusing. But this is very, very well, because every data, most of data contains that kind of feature. We have to learn this one, and that's one important issue there. About 20 years ago, many people misinterpreted this concept of stochastic trend. So many of the pioneering economic and financial research these days, their big portion is obsolete because of the ignorance of this kind of feature. But we'll get to that part. Okay. So many interesting work done. And then we extend the modeling from single equation to multiple equation. So very famous model. One of them is vector autoregression analysis. So that's one we'll be learning. And a little more advanced model called cointegration and error correction models. That's also very interesting. Subject we'll be covering. Let me very briefly explain why we need to model time series in a vector framework, not a single equation. Well, single equation approach is okay for some purpose, but in other occasion, multi-equation approach is better. So this is your consumption. This is your disposable income, right? Econ 101, you draw a 45-degree line, and consumption function is defined something like that. Right? So suppose actual consumption and disposable income has been moving that way over years. And suppose you are here 2012. What is the point? What would be the point, let's say, consumption and disposable income combination in 2013 and beyond? Hopefully we don't go that way, right? We get poorer and you're spending less. You don't want to do that, right? But you never know. Crisis, right? Is it more likely? Is it more likely? More likely? Which one? Well, as I said, it's uncertain, right? It depends. You all financial economists, when I ask something, you should say, well, it depends. Right? And then think. Right? Think very hard, quick. Will it likely that consumption will go up this way while disposable income stays. Is it likely? But that's my dream. My paycheck is fixed. But if I can spend more and more every year, well, that would be nice, right? That's utopia, right? East of Eden. Very unlikely. Also, well, disposable income is fixed. Is it more likely that consumption will fall? Well, it happened in Japan for the past 20 years. Their income, people don't spend because economy is toward long-term depression, right? But that's very unusual, right? So Abe economics, they do this one, right? To move this way, hopefully that way, right? So if you are looking at consumption series for the forecasting purpose, well, projecting that way is possible, right? But you know immediately when you look at the other series, disposable income, that's very unlikely. You can't sustain, this kind of increase in consumption forever, right? So that's the idea of modeling series more than one at the same time, right? So that's the subject of here, error correction model and so on. Okay. The most of the model is we classify it as a linear model, okay, linear model. And then we also cover some of the nonlinear model, which is very powerful. Some of them, like regime switching model, that has very interesting applications to model like business cycle, and also the state space model I mentioned earlier, using Kalman filter, and then final week. Okay. So tentatively, this is the coverage of the course, and those are kind of the methodology used in real workplace. So hopefully you find it interesting as well. Any question up to this point? Comments? Okay. Okay. Let's move to this side. Well, Ender's textbook, chapter 1, deals with the concept of difference equation. Difference equation is something that looks more like this one. Let's say T denotes each quarter. So third quarter of this year, second quarter, first quarter. Okay. The way the value X is determined this quarter is some fraction of previous amount. And the scale is determined by this parameter, for instance. And also the one determined 2 periods ago, and this fraction. And if you look at time subscript T here, the same thing, right? Epsilon is usually the universal notation for a disturbance term or error term. Okay, something that is not predictable. Okay. And so at time t, this quarter, we know this number because it's history, right? This is history. We know this number. Okay. If xt is generated by this process, okay, then in fact, if that is reality, then if you know these two parameters, you can determine this number next period, right? Because t plus 1, these are parameters. By definition, parameters are constant, something that doesn't change, okay? In this case, constant parameters. So suppose you knew that, and then this one is going to be x of t, which is known now, t minus 1, right? T plus 1, we don't know, right? So we need to characterize this one. So we'll get to that. But for time being, let's say we don't know that value at t plus 1. But suppose that on average, at t plus 1, epsilon could be positive, negative, or 0. But on average, let's say it's 0. Okay? So if you can't bet on particular direction, the safer bet is taking expectation, right? So on average, let's say if that is 0, then the value of x at t plus 1 is simply this times xt plus this times t minus 1, right? So that's a typical time series model. But the structure here, t minus 1, t minus 2, this is typical example of difference equation. So in economics, we use this type of difference equation often, particularly in macroeconomics analysis. And if you are working with continuous time model, then this one changes to a differential equation, right? But that part. So Ender's book starts with characterizing this type of difference equation. Okay. But as I said, there are too many things going on, because this is on the undergraduate course, we try to skip that part. It has been very important, but we learned many of those time series properties of difference equation these days, so we don't have to actually work out all those mathematical details of this difference equation. So we'll skip that part and move directly to chapter 2, which is about start with concept of stochastic process. Okay, so the terminology here, stochastic process is the family of random variables. So it's a collection of random variables defined on an appropriate probability space. Very broad definition. Okay, so there are infinite numbers, x, family of numbers, but the key word is a random variable. Random variable. So let me explain what is random variable here. If you look at here, that follows me. Okay. Typical notation is like x of omega in t. In that notation, there, I use x of t, right? But here, we introduce something new, omega. Okay, let me explain that. Where omega and t represents this one, sample space, this one, index set. So quarter, year, days, those are index set. And this one is called sample space. So explaining the concept of this one in probability theory it takes semester. So we'll try to avoid that. Okay, we'll skip that part. But let me explain very concisely what we mean by that. Let's say first, let's assume that t is fixed. So we are at current period t. Okay. Then what is x of omega? Well, there is a random variable. Random variable. For fixed omega, suppose you know omega, and then this guy is what we call realization. So story is like this. Stock price today is determined by, let's say, coin toss by the god. The god casts a dice or a toss coin. If it is head, it rises. If it is tail, it falls. Okay. So let's say if you observe head, let's say plus 1 point increase, and tail minus 1. So suppose this number t minus 1 was 10. Then what is the value of s at time t? So let's toss coin and then find which side, and let's say this one obviously is going to be 11, right? This event is related to omega. Once you observe this event, the outcome of coin toss, then you observe this number, right? That's realization. So you are observing GDP growth rate over quarters, right? Why those particular numbers in a sequence? Because of some underlying, we don't know exactly, but some underlying events defined over sample space. Okay. So randomness, we call sometimes this kind of variable as a random variable because that is associated with this omega. Right? So we are not going to worry about that omega much because in a time series analysis, most often we work with this realization. So stock price is observed, stock return is observed, CPI is observed, and then what? That's our starting point. Right? But the thing is, it is important to understand that the data we observe is a random variable. Right? Of course, we are living in just one word, right? One life. If we are allowed to live another life, starting from your same birth date, you may see different omegas and different life, right? You never know, right? But somehow someone cast the dice, and then here we are. Okay. So it is irrelevant in our proceeding. We will ignore this omega and just use notation x of t as a time series data. Okay. So the definition of time series is a realization from a certain stochastic process. Right. So it could be if you're lucky, then you can go infinitely to the past, or hopefully it continues to infinity. But of course, you're observing particular realization, right? That's your data. So because of this randomness, stochastic feature. This one is the term structure of Korea, Korea Treasury bond. So that's the bond issued by Korean government, Ministry of Finance and Strategy. Several companies report a thing called a spot curve. So if you look at time period like first quarter, second quarter, and the third quarter, term structure has been moving this way. Right? Why that happened? We don't know exactly, but some omega behind that. Right? This represents particular period, right? At particular t, different t. If you, let's say, look at same maturity, let's say 5-year period, this number, that number, of course, if you look at 10-year maturity, this number, and that number, if you look at those numbers over time, this data will look more like this one. Okay. So if you look at particular time t, that's upward sloping curve. But this is the way these numbers with different maturities, like quarter, half a year, 3 quarters, 1 year, 1.5 year, and so on, up to 20 years. This is when we experienced global financial crisis. So policy rate was lowered. So the whole curve actually went downward like this one. But of course, this interest rate and those interest rate with higher maturity is still high, very high. That means it's very steep, right? Very steep. But these days, because those gaps are very small, it's very flat term structure these days. So long rate and short rates are very similar, right? It is known in time series literature that if these rates are reversed, so long rate is lower than short rate, then that's indication of imminent business cycle recession. So time series analysts, sometimes your boss ask question about what is going to be the 10-year rate for the next 12 months. Okay? Then how do you respond to that? Well, you collect 10-year rate series and build a model, something like this one or different, and try to generate numbers forward, right? That's one way of doing it. Another way is, as we've seen, consumption and disposable income exercise. Look at interest rate sequence for other maturities as well, right? Or build some bigger, large-scale model where not only interest rate is determined by the model, but also GDP or CPI or other variables of interest at the same time. So there are many ways of generating a forecast, and we'll try to learn some part of that. Okay. But now let's narrow our discussion to estimating, let's say, just modeling one sequence. It's a 10-year rate. In the US, a 10-year rate is a reference rate. When you say interest rate in the United States, typically you say what is a 10-year Treasury bill rate, and also federal fund rate, which is policy rate. Very short end federal fund rate or 10-year rate. In Korea, our reference rate is usually 5-year rate. Previously 3-year rate, but these days 5-year rate. But probably we'll move that one to 10-year rate to make our rates comparable to those major countries. Right? Anyway, let's pick a 10-year rate. Then how to model 10-year rates to generate forecasts? Well, in terms of statistics, this is the way people do. Suppose we have cap T number of observations. So number of observation is, let's say, cap T. Okay? So small t runs from 1 through cap T. Theoretically, if you know t-dimensional probability distribution, you may able to say something about, what's the number of xt, let's say, next period. What I'm saying is like this. Let's say this is a single series. Okay? So I have number 1 through cap T. Okay? So I draw histogram of this data and find, let's say, average. If you look at just single-dimensional probability distribution like this one, let's say these numbers are normally distributed, then normal distribution. In normal distribution, we know the average and standard deviation will completely describe this function. Okay? Mean and sigma. If you know this, then you can tell, well, what is the value tomorrow? Well, if the old information you know is this, with a particular model, then perhaps if I were you, my forecast would be, well, because I don't know whether this will go up or down, I would say mu is next point. That's possibility, right? If you are pessimistic, well, this is sigma, well, this number or that number. Right? This is one way, if you know distribution. Right? Suppose you have different sequence or different numbers. Well, you can think of two numbers. So you have one set xt, t minus 1, right? So you have two set, right? So one on this axis and the other one this axis. What is a two-dimensional probability distribution? Because it's two-dimensional. What is the probability that you observe particular value of this and particular value of that at the same time? What is the probability? Suppose you can calculate that. Then something like this one, right? Two-dimensional probability. So why did you observe this cap t number of observations? Well, it's simple. If you know cap t dimensional probability surface or whatever, which is very difficult, right? Impossible. So that's not the approach. It says if it can be described by t-dimensional probability distribution, well, we can use that to build a model. But in fact, that's very difficult. We will focus on first and second moment only. But still, we can talk a lot about this particular time series. So the concept of stationarity, stochastic process, so random variable, is said to be strictly stationary if its properties are unaffected by a change of time origin. It is like, suppose you have distribution like this one for a particular time series, having average mu and sigma dispersion. Suppose you have different sample for the same data, but different period. But suppose that turns out to be, let me exaggerate a little bit. Obviously it has smaller mean, mu, and smaller sigma, right? So let's say this period is T1. This period T1 plus K. So K period shift. So 500 observation here, 500 observation here, but different time period. T1, this set, and T1 plus K set. If these are different, then what would be a forecast? Mu or mu prime? It's like speed of light being different today and tomorrow. Can you build physics? No, right? Water is frozen at temperature 0 Celsius, right? But sometimes, let's say it is frozen at minus 2 degrees in Celsius, sometimes plus 3 degrees in Celsius. Can you make physics out of it? Everything collapses, right? So that's the concept of stationarity. So what it says is, technically it says, even if you are shifting time axis, the joint probability distribution won't be changing. That kind of property is held, can be maintained, and we say time series is strictly stationary, but this is conceptual. More concrete example is, let's say T of 1, let's say T up to T of M, right, subscript. Suppose M is 1, so T1, case of 1. That means regardless of time period, first and the second moment, mean and the variance are the same. Mean and the variance are the same. If that's the case, series is stationary. Okay. I just noted here the definition of expectation and the variance. Of course, expectation, if X is continuous random variable, x times its frequency integrated from minus infinity to infinity. That's the definition of mu, right? And the variance is the expectation of the deviation from mean squared. Okay, so technically, x is the same x, and the mu this one. So deviation is squared, and then frequency distribution, the same one, and then you get variance. Throughout this lecture note, we'll be using gamma 0 as a variance, a particular time series. The reason being, well, the typical notation is, of course, sigma squared, right? But we'll be calculating, in some cases, covariances as well as variance. So if you're calculating covariance for xt and xt, that's a variance, right? But sometimes we need to calculate covariance between xt and xt minus 1, or xt plus k. So we try to use this one. 0 means t and t. Gamma 1 means covariance between two observations, one period apart. Gamma 2 means covariance between two observations, two periods apart, and so on. Okay. What if m is equal to, then this all covariance thing, not only the variance, but also the covariance. These are all the same. Here, one thing you need to pay attention is when m equals to 1 and m equals 2, we look at just these two cases. When I say mu and sigma, and here gamma 0, that's the variance, right? Variance. Or gamma k, covariance, right? We can't see any subscript t, no subscript t, right? Well, that's one of the key feature of when we define stationarity. But I think time is running out. I think we need to pause here and come back to this point. Okay. Looking ahead, I try to show some of the time series models we'll be covering, just representations, and then some of the motivations using a real example. So probably we'll be spending next time lecture hours explaining those other motivations, and then introducing EBIS programming and Gauss programming for Thursday lecture, and then continue to the discussion of the time series modeling next time. Always the first day of the lecture is very difficult because students are not fixed, and we enjoyed vacation too much, so we have built some unwanted habit. So hopefully we all can set our mode to class mode, so we can speed up our coverage more effectively starting from next time. Anyway, hopefully you can find this course interesting for your career building, and of course if you're really interested in empirical works in the field, I think this is not your option. This is kind of the very kind of requirement, whether you learn it from course or learn it by yourself, but you have to learn this technique, I think, anyway. Before I let you go, any questions? Foreign students, 2 of you, very brave, 2 foreign students. Okay. How about students from other college, other than College of Economics and Finance, or this college? Okay. Then I'll see you all next Thursday. Thank you.